Good morning, everyone. Good afternoon, everyone. So, the objective of the lecture today will be to demonstrate single point positioning. So, this is the program that we have supplied for demonstrating single point positioning. So, make sure you're on version 5, which is updated 11 April 2026 for the full capabilities as for now. So, overview of the software, the program. First, we have the setting part where we need to enter our navigation file, observation file, the measurement that we're going to use, which is CA code, C1 code, the frequency of the measurement, the date of the data, the elevation mass, and the total epoch. Next, we have some pre-processing where we include tropospheric correction models and some conversion of date, importing the right next observation file and navigation file. So after we select the observation file and navigation file, we will need to find the relevant measurement. So let me run it part by part. So, so here we will get all the settings. So if you run part by part, we could get need to import the file first. This will take some time, especially on reading the tropospheric model and also the observation and navigation file. Okay, so we have completed the part. You will see that the navigation file is a structure file and all the navigation data is in .nav. This is all the navigation information. Same for the observation, we have the GPS, GLONASS, and Galileo, but our focus today will be only on GPS. So this is all the measurements. But at the same time, this is just the measurement. We don't know the information of which measurement is which. That information is saved in STA. So you can open this and you could go to observation type. You'll be able to see row 1, column 1 is C1, column 2 is C2, etc. So if you look back to this one, you will be able to understand that, for example, this is the day of, this is the GPS week, this is the day of second of week, this is the PRN value, the satellite ID. This is starting from here is the measurement value, so we need to cross-check with the observation type. So for example, column number 4 is C1, column number 2 is C2, C8, etc. Okay, after we import everything, we need to find the relevant measurement and calculate the time of emission, which is what we are going to use. So we run until here. So this part actually selects the relevant measurement and calculate the time of emission. We need to do some converting and determine the size of loop. Starting from here, from line 53 to line 161 is 1 week loop where we calculate the position of every second. So for TT1 to epoch is the total number of epoch that we are going to plot. Epoch now is the time data that calls for the time data. For example, okay, we need to run this as a batch. So the final output should look something like this. You will see the X, Y, Z position fluctuating because we're using CA code and 3D difference relative to the first point of measurement. So here you could see the position keep fluctuating. 0 epoch refers to the first second of data. And this one will run until the finish 1000 or until the end of measurement. But while we're waiting, let me discuss a bit on what's happening inside the program. Okay. First, we need to determine what is the time that we are processing for. For example, okay, if you look at time data is based on time of measurement of where we measure the where we are measuring, we are collecting GNSS signals. So we select the one more because we need to process it second by second, epoch by epoch. So we need to select it first, and then we find which one is the observation related to the time, etc., etc. And then we start iterating the data. This is a quick preparation for the iteration. Okay, maybe some students will ask, why do we need to iterate? Because we are applying least square adjustment to determine whether to determine our approximate position. So in order to calculate using least square adjustment, there's two ways. One is to force it into a loop, a certain level, a certain number of loop. Like I want to loop it 10 times until, so it doesn't matter after 10 times does it converge or not. That's the result of 10 times. But the approach for this program is we will compare the second iteration with the first iteration and make sure that the second iteration to first iteration is the difference is below a certain limit that we have set. So that is actually at the part at the back lah. But I'll come back to this later. So in this iteration loop, the while loop, starting from line 63 to 117, the first we need to calculate the latitude, longitude, and height of the approximate coordinate because most of the models need to use latitude, longitude instead of Cartesian X, Y, Z. And then we prepare the matrices, matrix M, matrix L. I think Dr. Nam covered this in the last lecture. And then we need to, the next part involves error modeling for each satellite. So we need to call the satellite, the observation, find the appropriate navigation file. Okay, and then first we need to calculate the satellite clock errors because the signal is provided is sent slightly before our epoch time. For example, our epoch time is 1 second, but the signal is actually sent around 0.99998 seconds. So we need to correct for that time effect. It is also called segment effect. No, that is nothing. So here we calculate the satellite clock correction. Then this is just a constant. After we calculate the satellite clock correction, we need to calculate the satellite position using satpos. And then after we calculate the satellite position, we can calculate our sigma, our rho, which is the geometric range. But before calculating geometric range, there's one thing that we need to consider is the rotation of Earth. Because when we were presenting about the satellite computation, orbit computation last time, remember the effect where we put the Earth rotation rate and if we remove the Earth rotation rate. So when the Earth is rotating, the satellite is also rotating. So there's a relative motion between these two bodies. And this induces an extra measurement inside our signal, which is also called a Segnac effect. So for this Segnac effect is corrected by using this Earth rotation, and then we use Earth rotation minus the approximate coordinate in order to get a better geometric range. So up until here, we will get the geometric range, but we also know that our range is contaminated by errors like ionosphere and tropospheric errors. So here for this program, we do have the correction model applied. Ionospheric correction, we use Korbusha model to correct for the ionosphere. And tropospheric model, we use Sastamonian model with the help of global pressure temperature model 3, GPT-3. Okay, GPT-3 is not ChatGPT that you guys are familiar with. This is one of the global pressure and temperature model for the whole world. It gives us the pressure and temperature. So here we calculate all the errors and then we apply it back into the measurement. the L matrix. So the A matrix is basically what Totanum showed last time. The L matrix. After we have computed the values for all the satellites, we put them in one least square function, which is ATPA, ATPL. So after that, we will get the position x, y, z, delta x, delta y, delta z, and the clock. So we need to add it back to the approximate coordinate and look until uh, the condition fulfills. So what we do for least square adjustment in this case is we use the second iteration compared with the first iteration. Okay, or put it in other words, we use the current iteration compared with the previous iteration and make sure that the residual is below 0.01, so that if the difference between the two residuals are not too much, we can consider that it has converged, and the result is can be used. So the idea of least square adjustment, I'm not sure how many of you have been exposed to the idea, but the principle of least square adjustment is that the sum of squared residual must be minimal. So in order to realize that in the programming environment, we use the current iteration minus the previous iteration. So up until here is where we will get the position of our position. The rest from line 137 to 160 is more on plotting the data. So here you need to list the time. One line 137 is just the epoch here, written here. Difference 3D is to calculate the difference between the current position and the first position, initial position in 3D sense. And then the rest is just plotting. Okay, so that's the overview of the program. Is there any question before I move over to some extra demonstration? Okay, I'll take quietness as okay, everything is okay. So next I'll demonstrate some extra situation. Like in the default setting that I provided, we applied troposphere and ionosphere correction. What if these corrections do not apply? So okay, let me do one with the correction. Let me do one with all the correction on first, but only with short epoch, so it doesn't run for too long. Yeah. Okay, you can look that from this view, you can see that if we apply both correction, the consistency compared to the first initial position is around 1.5 meters. Okay, so now I wanted to demonstrate what if we don't apply tropospheric correction. So for example, we don't apply tropospheric correction. We only apply ionospheric correction. Okay, so for the first epoch, this value, we actually apply all the corrections, but we don't apply them for the rest of the measurement. So you could see after we remove the tropospheric correction, the value jumped from 0 to around 9 meters. by average. So we could say that tropospheric is one of the major correction. But compared to ionospheric, which one is bigger? Let us test. So in this case, we use ionospheric correction, but we don't apply tropospheric correction. Okay, the value jumped from 0 to 17, around 17, 18. So if you compare it to tropospheric correction, ionospheric correction seems to contribute more compared to tropospheric correction. What if we don't apply both correction? What is the effect? So the error would jump, in this case, if you don't apply any correction, the error would jump to around 26 meters compared to when we apply any correction. So this is what we could say about the accuracy of code positioning, especially when we don't have any correction model applied. Okay, up until this point, is there any questions?
No, sir.
Okay, if there's no question, I think the demonstration, that's all for the demonstration. If you have any problem with the program, just send a screenshot of the whole area and also your command window where they will come out the error code into the group, and we'll debug based on what's happening inside the group. I think that's all for today. So we'll see you guys next week, I guess. Thank you.
Thank you, sir.
Thank you.